Hello, it's Lars Skolding, dialing in from Singapore. I'm going to present the vector concept in the VHDL programming language. So let's get started. Firstly, I want to give a brief introduction of the vector concept. Then we're going to look at how to actually use the vectors, and then look at a little bit throughout. We'll look at coding examples, and then we'll end up with brief comments on subtype declarations, and then I'll summarize what we have been going through. So let's get started. So vectors are a type. It's basically a one-dimensional array, so very similar to other programming languages. In general, it comes in two generic flavors. It comes as STD logic, standard logic, underscore vector, or bit underscore vector. So these are just extensions of the normal types, standard logic and bit. It's particularly useful when handling signals. We'll see a few examples of that. The syntax for how we define and assign values to these standard vectors is as follows. So if you take this example from the VHDL Handbook, we can see we define an entity, my vector, and we can define that's my vector is a port. So we have input. The input is a standard logic vector. So the standard logic vector can go from 3 to 0. So the indexing goes from 3 to 0. So we have a 4-bit input. The output is a 1 down to 0 output. So the vector here is basically a 2-bit output. So far, so good. When we talk about indexing, then it's a little bit more tricky here in the VHDL language than in, for example, C or other purely software languages, because we have some sort of hardware abstract way of looking at things. Hence, the hardware index number in this case goes from 0 to 3 as well. If you put numbers on the addresses, then, for example, the address 3 has the value 1. Address 2, 0, and so forth. So this basically, from a hardware perspective, then this is what should be flowing on the chip. However, in a software description, then obviously we can do the indexing from here this way, or against the normal indexing. So there's two different kind of ways we can define a vector. Either it's basically here it's 3 down to 0, or we can write up or to 0. So if we just look at the 2 variation, then we go along the regular direction of index variable. So what we see here is that we get 1, 1, 0, 1. So that means that this is the most significant, the highest bit, so the most significant bit. Whereas if we define it as in down to state, then we go from 1, 0, 1, 1. So note that both declarations is possible. If you use the to declaration, then the first value need to be lower than the second value here. So there's low to high, or high down to low. Basically, in hardware or hardware community here, then the down to variation is the most used one. So that's the one we normally see in coding examples, etc. So it's important to also honor this principle when you start building code. That way you don't have to swap bits or buses around, etc. so making life a lot easier just to stick to some standard here. So if we further look at the example here, how to actually assign values to the vector constructs. So we have like architecture. So we have my example and my vector. So we have a signal C that's defined as exactly in the way we generally don't define vectors. So from 0 to 3. And we have an example going from 3 down to 0. So both of them are 4-bit buses. We can now just map A to C. Basically that will swap the direction of the bus, right? So the index 3 in vector A will be the same as the index 0 in vector C, and so forth. We can then also swapping back the vectors. So this is, I guess, something you can do if you want to not use this this clever trick here. So we simply just specify on our signal here that we can go from C to D in a regular way. So we use this assignment operator here, a mapping operator. If we then want to grab the most significant bits and pass them to a vector B, which would then in this case, previous example was defined as a 2-bit construct. Then we can grab from 3 down to 2, so that's 2-bit we are grabbing. Furthermore, there's other ways of managing assignment. So as you see, we can also use the map to operator in a slightly different way. So I believe there's an error in the notes where there's a bracket missing here. So you can have a list here where we then say so for basically this output vector here, then we have, if we can define as 1 down to 0, so the last 2 elements should be equal to A0, element 2 should be equal to 1, and element 3 should be equal to element 1 in vector C. Hence, like f will be defined something like this if you write it out. Right now we don't really know what C1 and A0 is. The clever thing is that we can use with the map to operator, we can use sort of a declaration called others, meaning that if we don't know the length of the vector or the bus where we want to assign things to, then we can just say others, we assign 0. So that means that we just assign basically 0 to the entire array here, and we don't need to specify the length of the array, so it's quite clever. Particularly, let's go on and talk a little bit about number representation here. So particularly for the bit underscore vector type, then there's 3 ways we can define what kind of underlying number system we're using. And this just happened by adding a B, or an O, or an X in front. So B is for binary, O is for octal, and X is for hexadecimal. So you can see here the way we use it. We define a bit vector, and we can assign, if we don't specify anything, then it will be basically assuming that it's a binary value we are passing. Otherwise we have to specify what values we are passing to the vector. It's also possible to join vectors, so like in concatenating strings in Excel, for example, then we use the ampersand symbol. So you can see here a little example where we define some 6-bit and 3-bit vectors and then do some manipulation. So for example, we can join like 0-bit with position 1 and position 2 in array or in vector C and D. Similarly, you can just simply join C and D. Note that you need to make sure that the lengths of the vectors matches. else might end up with overflows or missing undefined states, right? Similarly, we can dig out ranges, so 1 down to 0, and then concatenate with 0. So that's still 3-bit reassign. We can also append bits in front of a vector in case we want to extend the vector into a new construct. So that can come handy. Furthermore, if we want to extend bits, so we saw the last example showed that we are able to extend bits by just regular concatenation. There's other ways that's a little bit more clever. So the standard logic arithmetic package includes 2 very useful functions. So the extend function and the sign extend function. It's probably the latter we are going to use most, I think, since that preserves sign of the original vector. So basically, we can define the original vector, and then how long does the new vector want to be, or how long do we want the new vector to be. So you can see in the example here, it might be a little bit easier here to see. So basically, we have an initial vector set that's 3 bits, and we want to make it 6-bit. So we need to append 3 zeros. So like in the other example, this is exactly what's happening. However, if we had a sort of a minus 1, then as you see, like it can be represented by we need the first bit is basically the sign, right? So 1 1 1, and if we want to extend that 1, then we basically want to have 1 1 1 1 1 1 1. So instead of appending zeros, then it appends zeros if it's a positive value, or append ones if it's a negative value, right? So we preserve the sign. So that's actually what is right here. So you can do the Boolean math and stuff if you want to prove it out. We also have something called subtypes in this section. So a subtype is basically inherent type. So you can limit your own declared type to a subtype. So for example, it's very popular to use with integers. So you limit the range integer can take, a number of integers you can assign to your type. It's probably also quite useful for when you have some buses, and then if you want to pass signals through it, then you can basically define, for example, a initial type as an array, so of standard logic vector array here, so it's basically 6 bits, right? And then you make a smaller subset, which is 4 bits. I must say I haven't tried this code here, so from what I can find on websites, stuff like that is how it should be done. Any feedback is appreciated. So this is basically all this book about vectors. So thank you for listening. Further references, see the next page. Thank you for listening, and hope you add comments and feedback to this video. Thank you.